In the previous lecture, we have started to deal with the refraction in thick lens, and actually our actual problem is to find the cardinal points in the case of thick lens. Now today we will see, by utilizing the results which we have obtained in the previous lecture, that is the basic equation which we have find in the previous lecture, how we can calculate or how we can locate the cardinal points in case of a thick lens. You can see this figure. Actually this figure we have already discussed in the previous lecture. Here P is an object and Q is the image formed by the refraction in this thick lens. And after dealing with the refraction at the two curved surfaces of this lens, you have obtained a very important result between the relation between the U and V, and this result I have obtained in the previous lecture, and so you can see what this result is. In fact, the result is V equal to Cu plus D over Au plus B, where A is equal to P1 plus P2 minus P1 P2 times T dashed, and B is equal to 1 minus P2 T prime, C equal to 1 minus P1 T prime, and D is equal to minus T prime. And according to these values of ABCD, you can check that when you will find BC minus AD, the result will be equal to 1. In fact, in these results, you know P1 and P2 are what? These are actually the power of the refracting power of the first and second surfaces, and this T prime is what? This is actually T over N, where T is the thickness of the lens and N is the refractive index of the material of the lens. And we have also seen the two basic equations by applying the Gaussian formula for refraction through a curved surface, and one of them was this 1 over y1 minus 1 by u equal to p1, and second was 1 over b minus 1 over y1 minus t prime equal to p2. So these were the results which we have obtained in the previous lecture. Now let us see how to find the different cardinal points in the case of this thick lens. In this regard, first of all, we will see to locate the principal foci with respect to the poles. Actually, this principal foci will be again obtained not with respect to the poles, but here first of all we are going to find or locate the principal foci of this lens with respect to the poles O1 and O2. When you say poles, this O1 is the pole of first surface and O2 is the pole of second surface. So now you know, you have definitely an idea of the definition of focus of a lens, and according to the definition, actually a lens has two foci, and the first focus is defined in this manner that if image is formed at infinity, then the position of the object actually determines the first focus of the lens. So you can say if V is equal to infinity, then U will be equal to minus O1 F1. You can see the figure. This F1 is the first focus, so, and O1 is the pole. So distance of this first focus from the pole is O1 F1. Minus sign has been put here for the sign convention, because when you will measure the distance O1 F1, that will be in opposite direction of the incident ray, and so according to sign convention that will be negative. And so you can see from the definition of focus, when V will be equal to infinity, then U will be equal to minus O1 F1, and that is called actually the first focal length of the lens from O1. And according to the definition, how we define the second focus. You know, the second focus is defined as if you keep the object at infinity, then the position where image is formed, where the light beams actually converge, that is called second focus. So according to this definition, when u will be equal to infinity, then v will be equal to O2 F2. You can see here this F2 is the second focus of our lens, and so O2 F2 is the second focal length, and according to definition this is simply equal to the image distance v, but only when you will keep the object at infinity. Now we will impose these conditions on this equation A. You can see here. You can see if we will take v equal to infinity, so you can see the form of this equation when v will be infinity. To get v equal to infinity, definitely in RHS the denominator should be 0, because when you will divide a non-zero by 0, only then you will get infinity. So for v equal to infinity, this denominator au plus b must be equal to 0. So for v equal to infinity, au plus b must be equal to 0. And so from here you can see that au will be equal to minus b, and you know when v is infinity, then actually this u measures the first focal length. So what will be u? So u will be equal to minus b by a, and this value of u is nothing. This is simply the first focal length of our lens from O1. So you can see, therefore the first focal length measured from pole the pole O1. If you will denote this by beta prime, not by f prime. F prime will be denoted again for focal length, but that will be another situation. So we denote it by the symbol beta prime, and then you can see this beta prime will be simply equal to u, and that is equal to minus O1 F1 according to the figure, and that will be equal to minus b by a, and say this is equation 1. And again, according to this definition of second focal length, we will find the second focal length. According to this definition, when you will keep u equal to infinity, then the value of b will be simply the measure of the second focal length. And so you can see what will be the value of v when u is infinity. See this result A again. Simply we will take in RHS u equal to infinity, and then the value of v obtained will be simply equal to the second focal length. So you can say when, sorry, the page was just turned, so let us see. So you can see when u equal to infinity, then V equal to O2 F2. We have already mentioned it here, you can see, and that we will denote by the symbol beta, and that is actually the second focal length from O2. This is measured from the pole of the second surface O2, you can see here. And what will be this? We will, for getting the value of this V, we will simply put u equal to infinity in this result A. So you can see from equation A, so from A, what will be our result? You can see here that this V will be equal to O2 F2, and see the result. The result is Cu plus D over Au plus P. Actually, when you will put u, the value of u equal to infinity directly, the form will be indeterminate. So actually, to remove it from the indeterminate form, we will simply take u as a common factor both in the numerator and in the denominator. So let us first of all see this. Let us take u as a common factor. When you will take u as a common factor, the first term will be what? This will be a, and the second term will be d over u. And in denominator, we will again take u as a common factor, and so this will be a plus b over infinity. You can see that result. So here u and u gets cancelled, and now we will put u equal to infinity. So this will be c plus d over infinity and divided by a plus b over infinity. So this is simply a plus 0 divide, sorry, not a but c. This is c, not a. This is c. C plus 0 divided by a plus 0. And so this is simply equal to c by a. So if you denote the second focal length by the symbol beta, so you can see this beta will be equal to c by a. And what are the values of a, b, and c and d? You can see already we have defined it earlier. These are actually the values of a, b, c, d. So in this way, you get the expression for the principal foci with respect to the poles. Now the second calculation which we are going to make is regarding the principal points, or you can say linear magnifications. So principal points or linear magnification. Linear magnification. Actually, I hope you have an idea of the definition of magnification. It is when you say linear magnification, it is simply defined as the size of image divided by size of the object. So when the image is formed, you can see here, due to the refraction at the first surface, an image is formed which is Q1, and due to a refraction at the second surface, the final image is formed, and that is Q. And you know, if you want to find the total magnification, you will have to calculate the magnifications of the individual images. And as magnification is a multiplicative property. So after getting the values of individual images, we will simply multiply those magnifications to get the overall magnifications. So for this, let us consider that this M1 and M2 are the linear magnifications at the first surface and at the second surface. So let us consider it. Let M1 equal to magnification at the first surface. When you say at the first surface, it means this is magnification of the image formed at the first surface. And similarly, we consider that M2 is magnification at the second surface. It means it is magnification of the second image, that is Q. Now, according to definition of magnification, you can see M1 will be defined as Y1 over U. In fact, magnification is simply V by U, and you can see this equation, equation number D, which have been written for the first surface. Here Y1 acts like image distance and U is object distance, and magnification is simply the ratio of image distance and object distance. So this will be simply Y1 over U, Y1 over U. And similarly, what will be M2? You can see for this equation number C. Here at the place of V is V and at the place of U is Y1 minus T1, T prime. So according to definition, since magnification will be ratio of image distance and object distance, so this magnification will be simply equal to V divided by Y1 minus T prime. So M2 is V over Y1 minus T prime. Now actually these M1 and M2 are the magnifications of the first image and the second image, and you know, in case of a optical system consisting of which actually forms the different images, then the overall magnification is obtained simply after multiplying the individual magnifications, because magnification is a multiplicative property. Its total value is not obtained by summation, but it is obtained by magnification. So you can say, therefore, the overall magnification what will be the overall magnification? If we denote this overall magnification by M, then this M will be simply equal to M1 into M2. Definitely we have an idea of this. This is actually studied in +2 level. Now we will simply put the value of M1 and M2. You can see M1 is Y1 over U and M2 is V over Y1 minus T prime. So this will be Y1 over U times V over Y1 minus T prime. And actually to get a result in a particular form, we are going to find the reciprocal of M. Actually then you will get a simpler form of the result. So you can see, if we define 1 over M, what will be that? That will be simply U over Y1 times Y1 minus T prime over B. And this can be written as U over Y1. And now you can see, in fact here I have mentioned already that according to this formula which we have been written for the refraction at second surface, you can see 1 over b minus 1 over y1 minus t prime equal to p2. Actually this result has been obtained in the previous lecture, and so after simplifying this result you can see here that if you multiply this equation C both sides by y1 minus t prime, so after multiplication the first term will be y1 minus t prime over b, and in second term y1 minus t prime will cancel out, so that will be 1, and in the RHS there that will be p2 into y1 minus t prime. Here what we have done, actually you can see we have simply multiply this equation C both sides by y1 minus t prime, and so from here you can see this y1 minus t prime over b is equal to what? This is 1 plus p2 times y1 minus t prime. So this value of y1 minus t prime over b we will substitute here. So you can see this can be written as 1 plus p2 times y1 minus t prime, y1 minus t prime. Now we will simplify this result a little bit. You can there will be a lot of algebra, you can see it and you can do it yourself. So this will be 1 over y1 into let us simplify it 1, and when you will multiply by this p2 to the bracketed term, this will be 1 minus p2 times t prime and plus p2u. You can check it, and this will be equal to what? You can see this will be in fact p2 y1, not p2u but p2 y1. You can see here this will be p2 y1. Now we will multiply by this factor u by y1 to the bracketed term, you can see here, and this will be then what? This will be 1 plus p1u into 1 minus p2 t prime plus p2u, and you can check this will be equal to au plus b. I am not doing the complete algebra, you can do it. au plus b. Here a is defined and b is defined, and you can check when you will find the value of au plus b, you will simply get this result. Now in this result we will make the use of the equation. Actually this result has been obtained by using the results which we have mentioned here. You can see this result C and this result D have been used to get this value. So after use of C and D, this result has been obtained. Now from equation 5, from equation this A, see this equation A, when we will simplify this equation A, you can easily see what will be our result. So you can see from equation A, from equation A. From A, you can see according to equation A, this V is equal to what? This is Cu plus D over Au plus B. Au plus B. And you can write it V into Au plus B, Au plus B equal to Cu plus D. And equivalently, you may write V times Au plus B minus Cu minus D equal to 0. 0. And now you have seen earlier that here you can see BC minus AD is equal to 1. So from this equation, if we will find the value of AD, that will be simply BC minus 1. So according to equation B, from B, you can see what will be AD. AD will be equal to BC minus 1. BC minus 1. And we will actually use this result in this equation. So you can see it here that our result will be what? But before using this value, let us multiply this equation which we have obtained here, both sides by A. So after multiplying this equation both sides by A, you can see your result will be what? This will be AB into Au plus B minus ACU minus AD, and that is equal to 0. In this step, what I have done? I have actually multiplied this equation both sides by A. And now you can see this AD is equal to BC minus 1. So we will use this result here. So you can see this can be written as AB times Au plus B minus C into Au plus B, and that will be equal to minus 1. You can see the algebra. Actually here AD has been replaced by BC minus 1, and you can simplify it a little bit. You can see this will be Au plus B into AB. This is Au plus B, and Au plus B is common factor. So you can write it Au plus B into AB minus C, and that is equal to minus 1. And therefore 1 over m, which we have defined earlier, you can see it here. This is your 1 over m, and 1 over m you can see this is equal to Au plus B. And from here you can obtain the value of this Au plus B. 1 over m, which we have shown that this is equal to Au plus B. You can see this will be equal to what? This will be minus 1 over AB minus C, and equivalently you may write it as 1 over C minus AB. C minus AB. Actually, the value of 1 over m is more significant than m, so I am not writing here m. You may simply write m equal to C minus AB, but we will need actually the value of 1 over m for the further calculation. So I have written here only the value of 1 over m. And what will be the equation number? You can see this is just equation number 2. So we have obtained the linear magnification in terms of the constants a and b. Now, after getting the value of this 1 over m, or you can simply say m, we will be able to find the principal points of this thick lens. You can see this figure that these points H1 and H2 are actually known as principal points, and you know from the definition of principal points, actually the principal points are called conjugate points having the linear magnification equal to 1, that is m equal to 1. So in this condition, when we will find the distance of this H1 from O1, that will be simply equal to u, because in this condition we will have to take the value of 1 over m equal to au plus b. So you can see it here. See here, principal points. Principal points. Principal points H1 and H2. H1 and H2 are conjugate points. Conjugate points with m equal to 1, and therefore P prime, which is actually the distance of H1 from O1, that is O1 H1, that will be simply equal to u, for which m equal to 1 implies that u will be equal to 1 minus b over a. 1 minus b over a. You can check it. In fact, you have seen that 1 over m is equal to what? This is au plus b, and m is 1. So this 1 will be equal to au plus b, and from here you can see this au is equal to 1 minus b, and therefore u is equal to what? This is 1 minus b by a. So u is in this much, and this u is nothing. This is simply the distance of the first principal point from O1. So you can see this P prime is equal to 1 minus b over a. So in terms of the constants a and b, we have obtained the distance of the first principal point from the pole O1. Now this distance, the distance of the second principal point O2 from second principal point, not O2 but H2, from O2. That will be simply equal to V, for which M is equal to 1. So again you can say, again P equal to, I have denoted it by P, distance of H2 from O2, and that will be equal to minus O2 H2. Minus sign is due to the sign convention, and that is equal to V, and V for which M is equal to, this is just definition. When you take linear magnification 1, then the image distance is called the distance of second principal point from the pole. So we use that condition which has been mentioned in the definition of the principal point. So you can see here, when we will take this M equal to 1, then what will be actually the value of V? You can obtain it from here. You can see that this is equal to what? 1 over M is equal to 1 over C minus AB. So M will be what? You can see as 1 over M is equal to 1 over C minus AB. So when we will take M equal to 1, then C minus AB will be simply equal to 1. So you can see C minus AB equal to 1 when we take M equal to 1, and we take M equal to 1 according to the definition of the principal point to get the value of V. So you can see this will be AB equal to C minus 1, and therefore what is V? V is C minus 1 over A. C minus 1 over A, and this is actually P, which is distance of the second principal point H2 from the pole O2. So P is C minus 1 over A. So you can see from the equation for magnification, we have obtained the both of the principal points in terms of the constants A, B, C, D. Now you can get the nodal points. Nodal points. Actually here our lens is placed in the air, and you know if the medium in both sides of the lens are same, here that is in fact air, but it is not necessary that that medium should be air. But if we use the condition that the media on both sides of the lens are same, then actually the nodal points and the principal points coincide. You know it as the media in both sides of the lens are same. So nodal points coincide with principal points. This is a basic fact. Principal points, and therefore you can see this figure. I have actually shown this situation in this figure. This N1 is, your first nodal point, and h1 is first principal point. And you can see this point actually denotes the position of the first nodal point and also the first principal point. And similarly, this is n2, not n1. This n2 is actually the principal, n2 is second nodal point and h2 is the second principal, and both are coinciding. So you can say that here there is no difference between the principal points and the nodal points. And we have already calculated the position of the principal point, so it means you know what will be the position of nodal points. So you can say, therefore n1 is at h1 and n2 is at h2. You can see it. So in this way you can see we have obtained the principal points, the principal foci and the nodal points. In fact, now in the next lecture we will see what will be the focal length of this thick lens when that focal length will be measured from the principal points, not from the poles. Actually, in case of thick lens, it is convenient to measure the focal length from the principal points, not from the poles. But that we will see in the second lecture. We will also see the thick lens formula. That will be actually the final lecture on this thick lens.